All right, number 54. We're looking at for what values the constant m is f of x. Let's write this down here. We're talking about f of x equal to the combination of the two functions sine of 2x for all x less than or equal to 0 and mx where x is greater than 0. So we want to know where this is continuous and where this is differentiable. All right, so let's go ahead and graph this, even though it doesn't ask us to. Always nice to do. So sine of x equals 2x, x less than or equal to 0. Well, sine of 0 is 0. So we're talking about, normally would go up. We're talking about a function that looks like this afterwards. And when we've got this other line, this is just a line that goes to the origin. Maybe it looks like this. Oops, I actually went through the origin. Maybe it looks like that. Maybe it looks like this. Maybe it looks like this. Asking for where is this continuous and differentiable. As they all go through the origin, they're all going to be continuous. And so we can put this in any place we want. We have a slope of 0. We have a slope of plus minus 1. So in terms of continuity, so for A, f of x is continuous for all m in the real numbers. There's nothing we can't do there because they all go through the origin, and that will work out just fine. In terms of B, differentiability, we want to be differentiable. It can't have a corner, and to not have a corner, we need to have the same slope. So we've got this line that's coming up like this. It curves off and does that. But when it comes up, it's got a specific. So we can't do something like that. What we need is to have that line shoot off exactly where it's supposed to at the same slope. So what we're going to do is we're going to find the slope of sine of 2x at 0, and we'll just keep that, and we use that for m. So what we're going to do is we're going to take the derivative of f of x. This will be the derivative of sine of 2x, so that'll be the cosine of 2x, and by chain rule times 2. That'll be 2 times the cosine of 2x. And we want to evaluate this derivative. We'll evaluate this at x equals 0. That's going to be 2 times the cosine of 2 times 0, which is 0. Cosine 0. How about over here now? Here's the center. There's that cosine over here is your x value is 1. Which is going to be 2. So we need that to have the slope of 2. So this m needs to be 2. So we're going to write, how do they ask? What values is it differentiable at x equals 0? We'll write that f of x is differentiable at x equals 0 for m equal to 2. And it does say explain. M equals 2 because the slope of the tangent line to f of x at 0 is 2. obviously should qualify this. When f of x equals sine of 2x. Yeah, should have written that inside there, but that's all right. Tangent line to f of x equals sine 2x at 0 is 2. Hence, no change in slope. At x equals 0. Would imply no corners, cusps, that sort of thing. Oh, because I didn't really explain this one. It's all M and R. Well, we'll continue A. A continued. I should have put a because there. Because the limit as x approaches 0 from the positive side, because that's where it was coming from on this side, of f of x equals 0. So we're heading towards that point. And we're defined. And f of 0 was 0. This is for all f of x equals mx. Yeah. That ought to do it. That ought to do it. It's tough to tell how much information to put in and how much to leave out. Just comes with experience, and you can see even I'm not that good at it even after many, many years. (55) through 58. Determine where the function is differentiable, continuous but not differentiable, and neither continuous nor differentiable. So 55. Let's do a little reminder of ourselves. A is differentiable. B is continuous but not differentiable. Continuous but not A. And C is neither continuous nor differentiable. All right, 55. So we're looking at f of x equals 4. Got kind of a gap on my page here. Yeah. F of x equals x to the 4/5. All right, so we need to work this out. Let's go ahead and graph this. This is really the 5th root of x to the 4th, or the 5th root of x to the 4th. Use this one because you can take the 5th root of any x, positive or negative, and the 4th root, or the 4th power is going to make it positive. So we're going to have a very, so this would be x to the 5th, would be very, very skinny like that. And then to the 4th, what's going to come down, and it's going to sneak right back up. So we're looking at a point down at the bottom, very, very steep on both sides. So only look at this. We're continuous, everybody. So we are differentiable at x not equal to 0, because we're obviously continuous and smooth. Okay. Continuous but not differentiable at x equals 0, and neither continuous nor differentiable at no x. So, empty set. We've got number 56. About g of x equals the sine of x squared plus 1. And let's see here. Be wise to graph this with the calculator. I really wish I had brought one home. I don't have time to download one right now, so we'll just have to work this. So x squared plus 1 is differentiable everywhere. It's continuous everywhere. The sign of that, the only change here that's going to happen is when x goes from positive to negative. And when x is 0, it's the sine of 1. Sine of 1 radian. Interesting. Let's see. So x equals negative 1. No. X equals 0. Be the sine of 1. Sine of 1, 3, 1.5. So up here someplace. 1 radian is up there. So it's going to be nice and positive. So at x equals 0, talk about right there. And that's not quite at 1 yet. And it's going to oscillate back and forth. As x increases, we're going to go around the circle this way. So that means we're going to increase slightly. So it looks like we're doing this. As x goes negative, we're going to be increasing again. We'll be increasing this because the negative squared is going to be that. So this is going to reflect over the y-axis. So as x goes slightly negative, it'll still be positive. So it'll look kind of like this, I reckon. Someone would be so kind just to double check that on the calculator for me. That'd be nice. But you all would have access to a calculator for a question like this, I imagine. So we're talking about this point right here. We are certainly defined there. Because x equals 0, sine of 1 is perfectly reasonable. Don't get thrown by the fact that it's sine of 1. 1 is still, I mean, this is defined for all real numbers. We just usually have it in terms of pi. So this might be a little bit less than, it's in between pi over 3 and pi over 2. Right, so for A, we're differentiable everywhere but at x equals 0. And we're differentiable at B, continuous but not differentiable. And neither continuous nor differentiable, there is no point at which we are neither continuous nor differentiable. So again, pretty much same answers as the last one. I'm reading the answers right now. Said it is differentiable for all x. I wonder why that might be. Doesn't look like it's differentiable there. Almost out of time for the video. I'll double check that. It says nowhere. I wonder. I'll check it out.